Hello everyone, I am Dr.E.Purushotham, Associate Professor of Physics, Department of Physics. Today I am going to discuss about Galilean transformations. So in our previous classes we have discussed relativity, relative position, relative size, relative time, relative motion, frames of references. In that frames of references we have discussed about inertial frame of references, uninertial or non-inertial frame of references, and also we discussed about the theory of relativity. In that theory of relativity, the theory of relativity we divided into two types, that is special theory of relativity and general theory of relativity. So we discussed in our last class special theory of relativity and general theory of relativity also. So in our today's lecture I am going to start about Galilean transformation. You can see here, so Galilean transformation we can see. Yes, I am giving pen option right. So we are observing here, this is the Galilean transformation. Galilean transformation. Okay, Galilean transformation equations. So it deals with the objects or system which are speeding up or slowing down with respect to one another. So in our general theory of relativity we discussed the equivalence principle and everything, and the Galilean principle or Galilean transformation equations we are going to discuss. So Galilean principle, or it is also called Newtonian principle of relativity. Newtonian principle of relativity. It states that the laws of mechanics are the same in all the inertial frames of references. So what I am saying, the Galilean principle or Galilean transformation equations deals that the laws of mechanics are the same in all inertial frames of references. So Galilean transformation, the transformation from one inertial frame of reference to another is called Galilean transformation or Newtonian principle of relativity. So the transformation from one inertial frame S system to another S dash system is called Galilean transformation. It expresses the space time relation of an event in different references or in different frames. So Galilean transformation equations we can see here on the PPT. So this is let S, you can see in this figure, this is the S system. S and S dash, you can see here S and S dash be two inertial frames of references. So S and S dash are the two inertial frame of references. Let S is the rest, the reference frame S is at rest, and S dash, this is, and S dash be moving with a uniform velocity v along the x direction or along the x dash direction with respect to S along the positive x direction. What I am saying, let S and S dash two systems, these are the inertial frames of references. Let S be at rest and S dash be the moving with a uniform velocity v with respect to S along the positive x direction. So just you observe, compared to light velocity, the velocity of the system v is less than c, where c is the speed of light. Let the origins of the two frames coincide at time t is equal to 0. You can see here, suppose an event occurs at a point P. This is the point P. The observer O in system S, you see here, the observer O in system S determines the position of the event as coordinates x, y, z. The observer O dash, this is the O dash, the observer O dash in frame S dash, you can see here S dash determines the position of the event as coordinates x dash, y dash and z dash. Space transformation. So, this is the title of space transformation. The Galilean space transformation and time transformation equations are x dash is equal to x minus vt, y dash is equal to y minus y, z dash is equal to z. These are the space transformations. These are the space transformations. So, what I am saying, so here you see here the Galilean space transformation equations are x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z. These are the space transformation equations. But t dash is equal to t is the time transformation equation. You can see here, this is the time transformation equation. So, these are the Galilean transformation equations. You can see clearly here. So, Galilean transformation equations, just S system, this is the S dash system. Let S system and S dash system two inertial frame of references. Let S and S dash as the two inertial frames of references. So, S is moving, S is at rest, S dash is moving with a constant velocity v along the positive x direction. Let the velocity, the S dash system is moving with velocity v is less than light velocity or speed of light velocity, that is v is less than c. Let the origin of the two frames, so S frame origin you can observe here, this is the S frame origin, this is S dash frame origin O dash. The observer O in frame S determine the position of the event as a coordinates x, y, z. So, in this x, y, z. But in O dash observer observing at a point P, the in S dash system the coordinates x dash, y dash, z dash. You can see here. So, this x coordinate is from the S to observer O to at a point P, that is x. So, we know this is the x is equal to Vt, you know very well, velocity v is equal to x by t. What about x from this relation? X is equal to Vt. So, we wrote here this is equal to x is equal to Vt. So, this is from origin O dash to along x direction, this is the x dash coordinate. So, in S dash system the coordinates x dash, y dash, z dash. In S system the coordinates x, y, z. Then the Galilean transformation equations, the Galilean space transformation equations, x dash is equal to x minus Vt, y dash is equal to y, z dash is equal to z. These are the space transformation equations, but this is t dash is equal to time transformation equation, Okay. Next, failures of Galilean transformation equations. So, already we discussed about Galilean transformation equations. So, what are the failures in Galilean transformation equations? We can see here. So, number 1, failure to explain the Michelson-Morley experiment. So, we know very well about Michelson-Morley experiment. We discussed in our previous classes also. The Galilean transformation equation failures to explain the Michelson-Morley experiment. So, second one, in compatibility of the Maxwell equation. So, it is also failure to explain the Michelson-Morley experiment to determine the velocity and explain the Galilean transformation equations. So, this is the second one, failure to explain Maxwell's equation. So, failure to explain the Michelson-Morley experiment, and second one, failure to explain the Maxwell's equations. So, third one you can see here, it fails to accurately describe the motion of objects traveling at a relativistic speed, that means close to the speed of light. So, we can see here the second postulate calls for the same value of the speed of light c in S frame and also S dash frame. If we measured the speed of light in the x direction in the S system to be c, however, in the S dash system it will be c dash is equal to c minus v, c dash is equal to c minus v. So, what are the failures? Number one, it fails to explain the Michelson-Morley experiment. So, second one, it failure to explain the Maxwell's equations. So, third one, it fails to accurately describe the motion of the objects traveling at relativistic speeds. So, it very close to the speed of light. So, we can discuss about that a little discussion. The second postulate calls for the same value of the speed of light in C in S system and S dash system. If measured the speed of light in the x direction along the positive x direction in the system of S to be c, let in system S the light velocity c, however, in the S dash system it is moving with constant velocity v, then the resultant light velocity c dash is equal to, we are imagining c minus v, c minus v. So, due to these failures of Galilean transformation, we need clearly different transformation is required if the postulates of the special relativity are to be satisfied. So, we required the clearly a different transformation is required if the postulates of speed or special relativity are to be satisfied. So, the result of Einstein's theory was introduced now coordinate transformation called Lorentz transformations between inertial frames of references. Today, I am going to discuss about Lorentz transformation and Lorentz transformation equations. So, first of all, what is Lorentz transformation? You can see on the PPT, the Lorentz discovered a new transformation equations which are consistent with the new concept of invariance of the velocity of light in free space is called Lorentz transformation. Depending on the failures of the Galilean transformation, the Lorentz give a new transformation equations are called Lorentz transformation equations. So, that is why the Lorentz discovered the new transformation equations x dash, y dash, z dash and t dash equations which are consistent with the new concept of invariance of valency of light in free space. So, Lorentz transformation equations, you can see here on the screen. So, I am giving pen option, you see here. So, this is the Lorentz transformation equations. Let S and S dash, this is the S dash, this is S, this is the S dash. Let S and S dash are the inertial frame of references. S is the system, system means S, S dash is also system, two systems, that is two inertial frames of references. Let S be at rest, you can see this is the observer or origin O, this is S dash system, observer O dash. You see, let S be at rest, the system S is at rest or the inertial frame S is at rest, but the S dash system or inertial frame of S dash is moving with a uniform velocity v. So, it is moving with uniform velocity v with respect to S along the positive x axis. This is the positive x axis, it is moving along the positive x direction. What I am saying, let S and S dash be the two inertial frame of references. Let S be at rest and S dash B is moving or traveling with a uniform velocity v with respect to S along the positive x direction. So, let us consider a light pulse, any light or torch light, anything. Let us take a light pulse that starts at the origin O. You imagine the light pulse starts at O, origin O in S system. The observer will note that the light has reached a point x, y, z. From the origin, the light is moving and reached at a point P, let that is x coordinate. Like that, we can take at a point P the coordinates x, y, z, P, x, y, z. What I am saying, let us consider a light pulse that starts at a point O, that is origin O or observer O at t is equal to 0. The observer will note that the light pulse has reached a point P with the coordinates x, y and z, x, y and z. Okay, similarly, we have assumed that the origins are coincide at t dash is equal to t is equal to 0. Imagine the origin O is coincide with origin O dash at a time interval of t dash is equal to t is equal to 0. The light pulse also starts at the origin of S dash at t dash is equal to 0. Then the coordinate from O dash to that point P, we can take x dash. This is the x dash. Similarly, the point we can take P of x dash, y dash and z dash as shown in this figure. We can see. So, the transformation equation relating x and x dash can be written as, okay, what we are discussing. So, let S and S dash be the two inertial frames of references. Let S be at rest and S dash is moving with a constant velocity v along the positive x direction. Let us consider a light pulse that starts at a origin O at a time t is equal to 0. The observer will note that the light has reached at a point P, x, y, z. So, step 2, up to here you can observe this is the step 1. So, similarly, step 2 also we can observe, we have assumed that the origins are coincide. Just assume the origins O dash is equal to O dash coincide with each other, then assume the time t dash is equal to t is equal to 0. Then the light pulse also starts at the origin O dash, like in step 1 the light pulse starts at O and reached x at a point P, at a x distance at point P. The coordinates we have taken that is P of x, y, z. Similarly, the light pulse also starts at the origin of S dash at t dash is equal to 0, the observer will note that the light has reached the point P x dash y dash z dash. So, the transformation equation relating x and x dash can be written as. So, these are the transformation equation relating x dash can be written as x dash is equal to some constant. So, in Galilean transformation equation we took x dash is equal to x minus Vt. So, here this is Galilean transformation equation. This is low range transformation equation. We are taking x dash is equal to, this is the same, x minus Vt. We are taking one constant. The main difference is the constant. So, we are taking the constant. You discuss before that what we have taken. This is P x y z. This is P x dash y dash z dash in S dash system. So, we are giving the transformation equation relation x and x dash can be written as. So, in S system, due to the O observer, we are giving P x y z. In S dash system, due to the observer O dash, we are taking the same at point P, the coordinates x dash y dash z dash. So, we are taking the relation x dash y dash z dash and x y z relation. So, in Galilean transformation equation, we observed this is x dash is equal to x minus Vt. Just changing, we are giving the one constant extra, x dash is equal to k into x minus Vt. But in Galilean transformation and low range transformation also, it is not changing, y dash is equal to y and z dash is equal to z. But the time we can observe here, in Galilean transformation equations, t dash is equal to just we took t. But here in low range transformation, you can observe the t dash is equal to, in general, t minus one constant bx and also k. So, we are taking t dash is equal to k into t minus bx, we can see here. So, simply the transformation equation relating x and x dash can be written as x dash is equal to k into x minus Vt, y dash is equal to y, z dash is equal to z. So, t dash is equal to some constant k into t minus some constant b into x, where the constant values k is equal to 1 by root of 1 minus v square by c square, where b is equal to v by c square. Just substituting this k value at x dash equation and also in t dash equation k and b. So, we get, now substituting the constant k and b values in the transformation equations, we get x dash is equal to, I am going to take this one. So, x dash is equal to k into x minus Vt. From this relation, I took this one. Okay. So, what I am taking here? So, this is x dash is equal to some k into x minus Vt. Substituting k value, what is k? 1 by root of 1 minus v square by c square into x minus Vt. So, x dash is equal to x minus Vt all divided by root of 1 minus v square by c square. So, this is the x dash equation. X dash is equal to x minus Vt by root of 1 minus v square by c square. So, y dash is equal to y, there is no change in Galilean transformation and Lorentz transformation equation. Here z dash is equal to z, but t dash I am substituting here, t dash is equal to what I am taking here, some k into t minus bx. So, substituting all the value, what is k value? You see here 1 by root of 1 minus v square by c square into t minus what is b? B is v by c square. So, this is v by c square into x. So, this is equal to t minus vx by c square all divided by root of 1 minus v square by c square. So, this is the t dash equation. You can observe here t dash is equal to t minus vx by c square all divided by root of 1 minus v square by c square. So, the transformation, Lorentz transformation equations x dash, y dash, z dash, these are the space transformation equations. So, t dash is equal to, this is the time transformation equations. So, the transformation equations of Lorentz transformation equations, x dash is equal to x minus vt by root of 1 minus v square by c square, y dash is equal to y, z dash is equal to z, and t dash is equal to t minus v of x by c square whole divided by root of 1 minus v square by c square. So, these are called Lorentz transformation equations. These are called Lorentz transformation equations. So, Lorentz inverse transformation equations. If we assume that the system S is moving with a velocity minus v relative to S dash system. So, in previously the Lorentz transformation equation, the system S is moving, along a S dash system, this is O dash, with the constant velocity v, but here inverse, so minus v. If we assume that the system S is moving with velocity minus v relative to S dash along x direction, then the Lorentz transformation equation can be expressed as, so just to take at a place of v, you took minus v, at a place of v just to take minus v. So, in our previous, x dash is equal to x minus vt by root of 1 minus v square by c square. So, this is the Lorentz transformation equation. So, here x is equal to, just take at the place of x, x dash, at the place of v take minus v t by root of 1 minus v square by c square. So, this is x dash, this is x, not x dash, x is equal to x dash minus into minus plus vt all divided by root of 1 minus v square by c square. You can see clearly here. So, the Lorentz inverse transformation, Lorentz transformation equation x dash to x, inverse x to x dash. So, here y dash to y, y to y dash. You remember here z dash to z Lorentz, here z to z. Here also t dash to t, here t to t dash, inverse. So, the inverse Lorentz transformation equation, these are the space Lorentz inverse transformation equations. X is equal to x dash plus vt by root of 1 minus v square by c square, y is equal to y dash, z is equal to z dash, and the time inverse transformation equation, time inverse Lorentz transformation equation. This is T is equal to T dash plus Vx dash by C square by root of 1 minus V square by C square. So these equations are known as Lorentz inverse transformation equation. So you can see here Galilean and Lorentz inverse transformation equations we can observe at a place in one table. You see here, these are the Galilean transformation equations, Lorentz transformation equations, inverse Lorentz transformation equations. You see here x dash is equal to x minus Vt. Here x dash is equal to x minus Vt by root of 1 minus V square by C square, already we discussed. This is inverse. I am taking between Galilean and Lorentz transformation equation. So y dash is equal to y, here also same, y dash is equal to y, z dash is equal to z, here also same, z dash is equal to z. In Galilean transformation equation, t dash is equal to t. In Lorentz transformation equation, t dash is equal to t minus Vx by C square by root of 1 minus V square by C square. So these are the space Galilean transformation equations, these are the space Lorentz transformation equations, these are the time transformation equations. T dash is equal to t is the Galilean transformation equation in terms of time, that is the time Galilean transformation equation. Here t dash is equal to t minus Vx by C square all divided by root of 1 minus V square by C square is the Lorentz transformation equation in time, in terms of time. So this is the time Lorentz transformation equation. So we can compare between Lorentz transformation equation and inverse Lorentz transformation equation. So this is x dash to x dash is equal to x minus Vt by root of 1 minus V square by C square. Here x is equal to x dash plus Vt by root of 1 minus V square by C square. This is x dash is equal to y dash is equal to y, this is y is equal to y dash, this is z dash is equal to z, this is z is equal to z dash. T dash is equal to t minus Vx by C square, this is Lorentz transformation equation, t dash is equal to t minus Vx by C square all divided by root of 1 minus V square by C square. But in inverse Lorentz transformation equation, t is equal to t dash plus Vx dash by C square by root of 1 minus V square by C. Okay, you try to understand here the relation between Galilean, Lorentz and inverse Lorentz transformation equation. Simply you see here x dash is equal to x minus Vt, x dash is equal to x minus Vt by root of 1 minus V square by C square. Here x is equal to x dash plus Vt by root of 1 minus V square by C square. Here both are same in Lorentz and Galilean transformation. Y dash is equal to y, z dash is equal to z. Inverse you can see y dash is equal to y, z dash is equal to z. In Galileo t dash is equal to t. In Lorentz transformation t dash is equal to, this is the Lorentz inverse time transformation equation. This is the Lorentz time inverse transformation equation. This is the time Lorentz transformation equation, t dash is equal to t minus Vx by C square root of 1 minus V square by C square. So you can see here t is equal to t dash plus v x dash by C square divided by root of 1 minus V square by C square.